is Janet and Rabia.
Welcome to Everest Physics Academy.
In this video, we are going to define diffraction of waves. Describe the diffraction pattern observed through a narrow slit. Describe the diffraction pattern observed through a circular aperture. Describe the diffraction pattern observed through a rectangular aperture. Describe the diffraction pattern of a human hair. And prove that a light ray cannot be isolated.
We studied before the phenomenon of reflection. Reflection takes place when a wave bounces off an obstacle. Also, we studied the phenomenon of refraction. Refraction takes place when a wave passes from one medium into another. Now, let's study another phenomenon called wave diffraction. Wave diffraction is the bending of waves as they move around an obstacle or through an aperture. Observe this PHET animation. This animation shows a plane or a straight wave propagating from left to right along the surface of water, and then it passes through a small aperture. We observe that the emergent wave has a circular wavefront, and this wave has many directions. This phenomenon is called wave diffraction. Diffraction changes the shape of the wavefront without changing the frequency, the wavelength, and the speed of the wave. Any wave, such as light, infrared, radio wave, water wave, sound wave, etc., may undergo diffraction.
Diffraction of light exposes the wave nature of light. Let's take a look at Fraunhofer diffraction pattern associated with a single slit. Here we have a helium neon laser with wavelength 633 nanometers, a set of narrow slits. The width of each slit is less than 1 millimeter. We have a cardboard with a circular aperture. The diameter of the circular aperture is greater than 2 centimeters. And we have a screen to observe the light. Now, let's start our experiment. I will place the cardboard parallel to the screen and in front of the laser box, so that the laser beam passes through the circular aperture. What do you observe on the screen? We observe a bright spot of light having a diameter almost equals to that of the laser beam. As expected, light travels in straight lines. Now, let me replace the cardboard by a thin or a narrow slit. Observe. Okay, now what do we observe on the screen? We observe that light is deviated from its original path without being reflected or refracted. This phenomenon is called diffraction of light. Let's describe the diffraction pattern. We have alternate bright and dark spots or fringes on both sides of a central bright spot, which is called the central bright fringe. The central bright fringe is twice as broad as other bright fringes, and it is the most intense. Also, the fringes are aligned in the horizontal direction, but our slit is vertical. Then the fringes are aligned in a direction orthogonal to that of the slit. Now, what happens if I replace the slit by another one having a smaller width? Observe. The fringes become wider. Let's replace it by another one of a smaller width. The fringes also become wider. Another one of a smaller width. So, what do we conclude? We conclude that as the width of the slit decreases, the fringes become wider.
Now, let's summarize what we have learned from the experiment. If the laser beam passes through a circular aperture of diameter much greater than 1 millimeter, a spot of diameter equal to that of the incident laser beam is observed on the screen. So, light obeys the principle of rectilinear propagation. If the laser beam passes through a thin slit of width A less than 1 millimeter, we observe that light does not travel in straight lines. Instead, it deviates from its path without being reflected or refracted. This phenomenon is called diffraction of light. This figure shows what we observe on the screen for a thin slit whose diameter less than 1 millimeter. As we see, we observe bright and dark spots. This spot is called the central bright spot or the central bright fringe. This spot is called the first bright spot on the right side of the central bright fringe, and so on. This spot is also called the first bright spot, but on the left side of the central bright fringe, and so on. This point is called the center of the first dark spot on the right side of the central bright fringe, and this point is called the center of the second dark fringe on the right side of the central bright fringe, and so on. This point is also called the center of the first dark spot, but on the left side of the central bright fringe. Also, this point is called the center of the second dark fringe, but on the left side of the central bright fringe, and so on. So, on the screen, we observe alternate bright and dark spots or fringes on both sides of a central bright fringe. The central bright fringe is the most intense and has a width double that of the other bright fringes. The fringes are extended along a direction orthogonal to the slit. In this experiment, the fringes are extended along a horizontal direction. So in this experiment, the thin slit is extended along the vertical direction. This figure shows the spots corresponding to thin slits having different width. In the first case, the width of the slit is A equals 0.16 millimeters. In the second case, A equals 0.08 millimeters, and so on. In the last case, A equals 0.02 millimeters. We observe that as A decreases, the width of the spots increases. So we can conclude that the spots become wider as the width A of the slit decreases.
Focus, please. This is important.
Let's move to the diffraction through a circular aperture. Here is the laser source. Here is a magnified image of the circular aperture, and here is a magnified image of the screen. What do we observe on the screen? We observe a central circular bright spot surrounded by progressively fainter concentric bright and dark rings. Now, what happens if the diameter of the aperture decreases? Observe. The rings become wider. And when the diameter of the aperture increases, the rings become narrower. Now, let's summarize what you have observed. In the diffraction through a circular aperture, we observe on the screen a central circular bright spot surrounded by progressively fainter concentric bright and dark rings. The rings become wider as the diameter of the aperture decreases.
Let's study diffraction through a rectangular aperture. This figure is a magnified image of the rectangular aperture, and this figure is a magnified image of the screen. As we see, a rectangular aperture has a rectangular shape of length and width less than 1 millimeter. We observe on the screen two perpendicular diffraction patterns. Now observe what happens when we vary the width of the rectangular aperture. We can conclude that as the width of a rectangular aperture varies, the width of the spots vary.
Take a look at Fraunhofer diffraction associated with a human head. Here we have a helium-neon laser of wavelength 633 nanometers Now we have here a human hair. Now I will put the human hair in the path of the laser beam. What do we observe on the screen? We expect to observe a dark line down the center of the bright spot, but this is not the reality. Actually, as you see, we observe a diffraction pattern similar to that of the thin slit. Now the hair is vertical and the pattern is horizontal. What happens if I place the hair in a horizontal position? Look, the pattern becomes vertical.
One of the main questions: can we isolate a light ray? Let's study this diagram. Consider a beam 1 of light. This beam passes through a wide aperture since its diameter is much greater than 1 millimeter. So, it obeys the principle of rectilinear propagation of light and it emerges from the aperture with a diameter equals 2 centimeter. Now, consider beam 2. Similarly, beam 2 passes through another wide aperture since its diameter is 1 centimeter and it obeys the principle of rectilinear propagation of light and emerges from the second aperture with a diameter equals 1 centimeter. Now, beam 3 passes through a small aperture since its diameter is less than 1 millimeter. So in this case, this beam will diffract and emerges from this aperture in many directions. Then we can conclude that we cannot isolate a ray of light. Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button and share.